In this next question, we have 4-nitrophenol. So clearly the OH of the phenol is the group with the higher priority. So 1, 2, 3, 4. Or you could do the other way around, 1, 2, 3, 4. You're still going to get this as position number 4. So NO2 is the nitro group. The OH bonded to the benzene is the phenol. So 4-nitrophenol can react with 3 different reagents. So complete the table. You gotta draw the structures. If I were you, I would go for skeletal formula, but of course they say, draw the structure. So you can draw skeletal or displayed or structural. It's really up to you. But you're in A2 chemistry now. Structures are more complicated. Skeletal is probably the one I would go for. That is the one that I always advise students to go for. It's the fastest, it's the most elegant, and every single A-level student should be able to do skeletal formula easily if you want to do well for organic chemistry. And you also have to identify the non-organic product. This is quite unusual. Usually the question you just say organic product. They don't usually focus on the inorganic. Inorganic means non-organic product, but since the question asks you for that, we're going to do exactly that. The first one is a sodium metal. So what happened with alcohol, including phenol? When it reacts with sodium metal, you will behave just like water. So what happened then is you will get a sodium alkoxide. So you get RO minus and you get Na plus. So where does this H go to? You will produce a hydrogen gas. This is just writing a general equation. Of course, then you have to balance your equation. One OH group will give you, basically one hydroxyl group will give you half mole of H2 molecule. And you will see that this is a redox reaction, as that is sodium 0 going to sodium plus 1 there. And of course, if you can find the oxidation, there is an increase in oxidation number. You should be able to see the reduction as well. Hydrogen plus 1 going to hydrogen 0 in the element. So that is your reduction, oxidation and reduction in the same reaction. This is a redox reaction between metal and alcohol. So your identity of non-organic product will be H2. They say identify, they don't say draw the non-organic product. So I can just write down H2 as a gas and draw the structure of the organic product. So there is nothing wrong with the nitro group. So maintain the nitro group. And what I get is I get the sodium alkoxide. This is called sodium phenoxide. So the way to spell it is phenoxide. But of course, it's not just a normal phenoxide. It's going to be the 4-nitrophenoxide. So this is sodium and then 4-nitrophenoxide ion. Next bit is Br2 aqueous. This is very specific to phenol chemistry. So we know that phenol highly activates at position 2, 4, and 6. So 2, 4, and 6 substitution. But then the fourth position is being blocked by the NO2. So you're going to get full substitutions at position 2 and position 4. You can think of this as 2, 4 or 2, 4. Doesn't matter. What's going to happen will be your substitution reaction. So you will kick out the H plus and you replace that with Br and Br. The OH activate at those positions, and you also have your nitro group uninterrupted. So you kick out the H plus, you replace the H with the Br. So you remove the H plus, and you're gonna get HBr as a gas, or probably even aqueous solution is acidic. But where this reaction give out these fumes there, you're gonna decolorize the bromine water from orange yellow to colorless as the bromine reacts. This is your source of Br minus because you have substituted electrophile, the Br plus from the Br2 with the, you substituted the H on the benzene with the Br plus electrophile essentially. When you are asked about equations, you can of course write a balanced equation for this as well, even though they don't ask you here, but you never know when they ask you. So you have this H and this H, which we're not gonna show, I guess. So that phenol there, there is an ugly phenol there. So there's a better phenol, and then I have Br2. I want to add Br plus and Br plus, so I must have 2 Br2, and then I maintain my original NO2 unreacted, and then I've added a Br and a Br there, the OH maintained there, and I get 2 HBr because I kick out the H plus and the H plus I have Br minus and the Br minus. As I put the Br plus and the Br plus there, so this is the balanced chemical equation. What else can I say? This is a redox, by the way, because very clearly you can see the Br0 and you can see the Br minus 1 there. Okay, so I don't want to talk about the other stuff, but you know, the fact that this carbon there loses the hydrogen there, so that is your reduction. Loss of hydrogen is reduction. So loss of hydrogen is reduction. And is that reduction? Probably not. It's quite hard to see what's happening there, isn't it? No, that's not right, because it cannot be a reduction, since the bromine 0 going to bromine minus 1 is definitely your reduction already. Well, I don't want to speculate what happened to the other one, but you can imagine that, you know. Oh, that was right. Yeah, because there was loss of hydrogen. What am I talking about? Oh, carbon loses the hydrogen. Loss of hydrogen is definitely oxidation. So I was right all along. I don't know what I was talking about. I was lost looking for the oxidation. So gain of hydrogen is reduction, loss of hydrogen is oxidation. You get a redox reaction overall because you have oxidation and reduction in the same reaction there. There's your inorganic product there. Wouldn't be too sure whether it will come as a gas. Perhaps not. Perhaps I just write HBr aqueous solution. That is definitely true, as the HBr can dissolve in the water to give me this acidic solution as well. Last but not least, I have the COCl, and that is not going to do anything on the NO2 group. And I must add something. The NO2 group is 3 and 5 directing. So 1, 2, 3, 4, 5. So these two positions being substituted is not only directed by OH, but also the NO2 kind of agrees that the substitutions should be directed at these two positions there. This is an acyl chloride. So acyl chloride will react definitely with the phenol, and the phenol will form an ester. This is a CH3CO from the CH3CO fragment. This is what you call a condensation reaction. As the phenol loses the H, you will lose the Cl, and the H come from the phenol, and you will kick out a small molecule HCl condensation reaction. And this will be given out as an aqueous solution because you didn't use this in water, nor water, because very sensitive to water, easily hydrolyzed. So you don't mix water into this one. So this thing is not going to come out as HCl aqueous because there is no water to begin with. So, you know, it'll come out as this steamy white fume. You see a steamy white fume because this reaction is very, very exothermic, as the acyl chloride is very, very reactive. All that for 4 marks there. Now the next thing, 4-nitrophenol can also be used in the synthesis of dyes. So usually we talk about azo dyes, where you have nitrogen like this, and then this thing there is the azo dyes. So what do we have here? Well, we have the final product. I guess we have to work backwards. So your phenol is here. Your phenol will activate substitution at position 2 and 4, and they happen to also be directed by these NO2, which will also direct it to position 3 and 5 relative to itself. This is 1, 2, 3, 4, 5 for the blue, whereas the green one is in direct position 2, 4, and 6 relative to itself. So green one is 1, 2, 3, 4, 5, 6. The fourth one is being blocked there. So what we see here is the substitution at this position 2 there, and that is not too surprising. What we get there must be this diazonium. So that thing there must be your diazonium salt. So F must be diazonium, and it is a salt. So just following what we had seen in the final product. Don't know why my benzene is very, very ugly there. So there's much better benzene, NH2, SO3 minus, Na plus. Always been my habit to draw the charges in circles. I don't have very good eyesight, so you know I tend to miss this thing if I don't circle it. Okay, not too sure about you. So this is NH2, doesn't do anything. But the diazonium comes from down there. You don't need a different color. I'm just drawing it as different colors so that you know you can see very clearly what is going on. Diazonium, the salt comes from these Cl minus like this. They are not bonded together, just like these are not bonded together. I mean, not directly bonded like covalent bond, but you have ionic bond. You also have ionic bond there. How do you get the diazonium salt? Well, this is forming the salt. Forming the diazonium. How do I know that? Because this thing has the SO3 minus Na, this thing has the SO3 minus Na. So what I'm going to do is draw the benzene ring again. No, that doesn't look so good. Okay, so that is our NH2, that is our SO3 minus, Na plus, and keep everything else the same except for the diazonium fragment. So this diazonium fragment will have come from phenylamine as well. Yes, you have many phenylamines, but this is the one that is the position that will form this thing here. If you look at the molecular formula, 6 carbon, so 6 carbon, that's all right from the benzene. 8 hydrogen, so there is 1 and 2 hydrogen on the benzene, no other hydrogen left, so 2, 4, 6, 8, so there are 8 hydrogen. Nitrogen, there are 3, 1, 2 and 3, and then SO3 minus Na plus, that thing is probably obvious. So there are many phenylamine here, NH2 bonded to the benzene ring, but this is the one that will give you diazonium at this particular position. And you would need HN, well actually you need NaNO2, sodium nitrite. Nitrite is actually a 14 to 16 years old chemistry content, and you've learned this as table of ions from O-level, IGCSE or GCSE level chemistry. You add that with HCl, and cold conditions 0 to 5 or 10 degrees Celsius will be alright. Typically we just use an ice bath, so let's just say 0 degrees Celsius, probably better to prevent the nitrogen gas from being evolved or from being released. And this thing before they react together, usually we deprotonate, because we're gonna make it a much better nucleophile. So you deprotonate with NaOH aqueous, and you will have O minus, and that will greatly increase the electron density in here and make it richer in electrons to undergo the electrophilic substitution at this particular position, making this reaction even more reactive. Suggest the structures, that one is done. Suggest reagents and conditions for step 1. Step 1 was the diazonium salt formation, so I already did that, NaNO2 and also HCl aqueous. And do not forget, the conditions have to be kept cold, so usually we use an ice bath for this. As for the step number 2, this is this reacting with this. Like I said, we have to deprotonate this with NaOH, so we need NaOH aqueous. And if you continue to leave this at 0 degrees Celsius, they are not going to want to react. So we want these to react with these. So going from 0 degrees Celsius, we're going to warm it up slowly. So the condition will be, take away the 0 degrees Celsius, so warm up slowly, mix and then warm up slowly. Mix and then warm up slowly from 0 degrees Celsius to room temperature. So you don't want to heat it, you want it to react slowly, and then they will form you the colorful azo dyes. So you see from something colorless, combining together to give you something colored, because azo dyes are colorful. And that's the end of that 9-mark organic question there.